Hello and welcome back to CS422. Today we want to recap and talk in more elaborate detail about Oracle computation. And as you recall, the pedagogical concept underlying this entire lecture is to avoid Oracle Turing machines and any other kind of Turing machines, although their introduction and invention by Alan Turing was a great achievement and progress, and underlies still nowadays the development of digital computers. But from a pedagogical perspective, computer science has moved on, and nowadays people don't really design Turing machines. Actually, when Turing invented this machine now named after him, he did so as a formalization of a computer, where computer was a profession, some job that was performed by employees doing calculation. That was called a computer. And Turing formalized that into the concept of a Turing machine that was later became the actual, what we call a digital computer. But nowadays, for pedagogical reasons, let's turn things upside down. What you all know is programming in some imperative programming language. And so we have designed this course in order to develop the theory of computation from the perspective of actual imperative programming. To this end, we have introduced, as you recall, the while programming system, which was a very, very basic programming system, very simplistic, down to the core, only very few operations, increment, decrement. So let us review that and then proceed from there. So what you see here is, for your reminder, the syntax of while programs with the two increment and decrement operation, only non-negative integers, a loop construct and a while construct, which gave the name to the programming system. And we saw that this is fairly powerful, and for technically it is actually equivalent in its power to a Turing machine, but much more easy to digest from nowadays perspective of a computer science student. And then we want to enrich that with a concept of an oracle. And oracle was also introduced by Alan Turing in his PhD thesis. Much later than once he introduced the Turing machine, he pursued a PhD at Princeton under the supervision of Alonzo Church, and there he introduced and studied and investigated what we nowadays would call Oracle Turing machines. But in this course, instead, we're going to study Oracle while program. So what is an Oracle while program? An Oracle while program is simply an ordinary while program, but with an additional instruction, namely evaluating a function, a certain fixed arbitrary total function. Now, why would we do that? One motivation is, for example, to study the power of calls to external functions, functions that may or may not be actually computable. So the question of whether and how such a function can be implemented and expressed in while programs is not the subject. Actually, the interesting things happen only when this function is not computable. Because if it is computable, then we can, of course, replace any call to that function by the actual execution of a code of that function. Whereas if the function is not computable, then there is no such code, and then being able to make such a call to a function as a black box, as an oracle in the original sense of a Greek word, right? Oracle of Delphi, then it actually enhances the computational power of while programs. Oracle programs may be strictly more powerful than regular programs. And let's investigate how much more powerful and what that depends on. And so you recall that we've already introduced notions of reductions as a means of comparing the undecidability of decision problems, L and L prime here, using this notion of a reduction. And one particular property of this reduction was that the result of the kind of reduction after the translation, the answer must be given immediately, directly, and cannot be post-processed. So this is kind of a reduction means one can perform some pre-processing. The pre-processing means transferring the input argument X using some computable translation pre-processing function F to obtain a new data item Y. And then the reduction must satisfy that X belongs to L, so it must be a positive instance if and only if the translated element Y is a positive instance of L prime, if and only if. And yes, as I said, so this is kind of one way of looking at this is that we can do some pre-processing of the argument X to obtain a new argument Y, but there's no post-processing. So if the new argument Y belongs to L prime, then the answer is and must be true also for the original argument and vice versa. Okay, and we want to generalize that and also allow for some post-processing. Furthermore, we want to allow for some adaptive making additional use of the new decision problem L prime, and that's exactly what Oracle programs do, and this leads to the notion of reduction, which is sometimes called Cook reduction, as opposed to this reduction, which is called Karp reduction. Okay, and since we're already on the way generalizing, we're also going to generalize from decision problems, L and L prime as subsets of natural numbers, where the answer is true if the element belongs to L and false if the element does not belong. Generalize that to function problems, maybe such as this one, right? And so the generalization is as the following. And the functions we're going to consider here is, for example, make an Oracle call to the characteristic function of the primality problem. That is, using invoking this Oracle will tell the invoking while program whether the argument xi is a prime number or not. The second example is the characteristic function of the halting problem. So invoking the Oracle in this case tells the calling while program whether the given natural number argument is the code of a terminating while program or of an unterminating while program. And observe, here it tells both. If it is a terminating one, it will answer yes. And if it is a non-terminating one, then it will answer no. As opposed to previously, we could only get a positive answer if it terminates and get no answer. So you can already see how this extends and enhances the power of computation, having Oracle access to the characteristic function of the halting problem. And the third example we consider is the totality problem. And again, as you recall, we explored and shown that the totality problem is strictly more undecidable than the halting problem in the sense of this reduction here. And so similarly, being able to make a black box Oracle call to the totality problem will be able to tell us whether the argument xi is the code of a while program that terminates always for all possible inputs or not necessarily for all. So again, the latter part is also important. If it's does not terminate for all possible, then the calling Oracle while program still gets an answer and can use that answer for post-processing or other purposes, and it actually can make a second call to the function based on the previous result of the previous one. So adaptively re-querying the Oracle is perfectly fine an arbitrary number of times as long as it's a finite number of times, because the while program, the or while program should supposed to terminate after all. And now we're going to generalize this previous notion of reduction of decision problems to reduction between function problems in this very sense. So for two total function problems, psi and phi, we say psi is at most as difficult as phi, or as function problems, not anymore as decision problems. If there exists a while program with oracle phi, the second one, that is able to compute the function psi using, possibly repeatedly using the oracle phi as a black box function call. Okay, so again, now we have introduced something using a terminology of a relation, a partial relation, and we should verify that this terminology is justified, and we should verify that it satisfies all the requirements of a partial order. Specifically, it should be reflexive. Any problem should be decidable. Any function should be computable with itself as an oracle. I'll give you a minute to think about and verify that. It's pretty obvious. And transitivity. So if one function is computable with the second function as an oracle, and if the second function is computable with help of a third function as an oracle, then the first function is computable with the third function as oracle. Again, I'll leave it to you to verify that this is indeed the case, and thus that this notion of reduction is constitutes a pre-order and in particular satisfies transitivity here. Okay, so now we can rephrase our initial results about reduction, curve reduction between decision problems in terms of this reduction between function problems using the characteristic function. Characteristic function is our standard way of identifying decision problems with total function problems, right? I also like to point out the similarity between these all these various notions of reduction to comparing the cardinality of sets. For those of you who are familiar with set theory, where one also studies sets of different cardinalities, basic or the finite sets. Then there are the first infinite set, the countably infinite sets, such as natural numbers, or the set of integers, or the set of rational numbers, or the set of finite binary strings, all countably infinite, all having the same cardinality, where same cardinality means there's an injective function and there's a surjective function, which is equivalent to having a bijection according to Cantor's theorem. And then there are the even larger sets, such as the set of real numbers, the power set of natural numbers, and so on. And the hierarchy goes on. And as we're going to see, there's a similar hierarchy climbing up with oracle-wide programs of more and more undecidable problems. And this is called the arithmetic hierarchy. So in order to get there, let us first study some higher order types of halting problem. You remember the halting problem is a subset of natural numbers, named the set of all codes of while programs that terminate, let's say, on the empty input. It doesn't really matter on which input, let's just say on the empty input. The higher order halting problem is a similar question, not for while programs, but for oracle while programs. So H with superscript L is the set of all codes of terminating while programs, but now terminating Oracle while programs with Oracle L on the empty input or not. So let's study that. And the first thing to notice is that the original proof of undecidability of the ordinary halting problem carries over to undecidability of Oracle, terminating of Oracle while programs. Maybe first thing is we still have an interpreter, namely while Oracle while program with Oracle L can semi-decide whether a given Oracle while program with Oracle L terminates or not. Let me say it again. So this is a problem given an Oracle while program with Oracle L. Does it terminate? And this can be semi-decided by an interpreter Oracle while program, which now again, of course, also needs Oracle access to the same Oracle as the while program it is supposed to simulate. So if we consider Oracle while programs with some Oracle L in order to simulate that, then also the simulator needs access intuitively to that Oracle. And having that access, given that access, indeed, it can semi-decide the termination by interpretation. And however, it cannot decide it. Similarly, that for the case without oracles. So the statement second part says the oracle, higher order oracle halting problem is not decidable by any oracle program that uses the same oracle, can make oracle calls to the same oracle. And this can be now formally expressed in using that relation. As you recall, this means that the characteristic function of the halting problem for while programs with Oracle L cannot be decided, right? This means this cannot be decided by an Oracle while program with Oracle L. Okay, so in this sense, the Oracle determination of Oracle while programs is also undecidable by Oracle while programs. And now we can iterate that scheme because we know that the termination of a while program without Oracle is decidable by an Oracle program with access to the Oracle halting problem. So given access to the halting problem as Oracle allows, obviously, reflexivity to determine the termination of a while program without Oracle. And this gives rise to this hierarchy that I'm going to explain now. So the first step says the ordinary halting problem is cannot decide whether the termination of a halting problem for oracles, for while programs with halting oracle. And this means consider the halting problem for while programs with halting oracle and consider the termination of these oracle halting problems. Okay, so let me say it again because this is probably confusing. So this means the halting problem, the termination of an oracle while program that can have access to the halting problem as an oracle. And this means termination of a while program that can have oracle access to the oracle, which tells about the termination of a while program that in turn has oracle access to the ordinary halting problem. Okay, and this symbols means that this one is strictly harder, and this one means that it is strictly harder than this. And so by continuing this, we can climb up hierarchy level by level. So a tower of 4 halting problems is strictly more undecidable in this sense than a tower of 3, and so on. Tower of 5 strictly more than a tower of 4, and that's going to be the arithmetic hierarchy that we now introduce and formalize on the next slide. So And I'm going to call this the semantic arithmetic hierarchy for reasons that will become clear on the next slide. So for now, just consider this to be the arithmetic hierarchy because they're going to be actually equivalent. And we define this formally by structural induction, starting with the ground level. The ground level of the arithmetic hierarchy is the collection, the family of all decidable problems, of all decidable subsets of natural numbers. And we use three notions for that, for reasons that become apparent in a few minutes, namely delta 1 and sigma 0 and pi 0. And the reason is that this then leads to a very elegant induction. As you may recall, sometimes induction becomes much easier or elegant when using the right induction start, and that's what we do here. So these are three different terminologies for the set of decidable subsets. So this is our subsets of the power set of the natural numbers. Okay, and here's a picture for that. This is the basic, the ground level, the decidable ones. And from there we climb up to the semi-decidable ones and the co-semi-decidable ones, which are the complement of the semi-decidable ones, and those that are decidable with respect to with the help of oracles. And that's our next line here. So delta k plus 1, so the induction step kind of delta 1 has been defined. Delta 2 is then defined to be the set, again, the collection of all subsets of natural numbers that are decidable with oracle access to sigma k. So which is consistent with this definition in case, for example, when k is equal to 0, then this is recovers this definition. And observe that this is the same as those that are decidable with oracle access to any oracle in pi k, because for now, because the two are the same, but we're going to define sigma 1 and pi 1 inductively in just a minute, so bear with me. So this gives rise to this hierarchy, to these levels. So the second level means that these are the problems that are decidable with respect to, with help of a oracle in sigma 1, and delta 3 are those that are decidable with the help of an oracle in sigma 2. But I haven't yet told you about sigma 1 and sigma 2, so let me do that. First, record that this delta part of the arithmetic hierarchy are closed under complement. So if there's a subset of natural numbers in the kth level, then also the complement of that subset belongs to the kth level is also decidable. And why is that the case? Because for the same reason that the ordinary decidable problems are closed under complement, one can change an oracle program that computes, that decides the set, into a while program that decides the complement of the set by simply reverting the final instruction that returns 0 or 1, depending on whether the input belongs to the set or not. And reverting that just decides the complement. So that's ordinary, our ordinary closer under complement generalizes in that sense. But now I still owe you the definition of sigma 1 and sigma 2 and so on, and the definition of pi 1 and pi 2 and so on. And these definitions are again proceed by a structural induction on k, the level. So let's first have a look at the at sigma 1. What is sigma 1 here? Sigma 1 means that k is equal to 0. That means these are the problems, the set of subset of natural numbers that are semi-decidable with oracle to sigma 0, and sigma 0 means decidable. So now recall that having Oracle access to a decided problem does not increase the computational power, because any Oracle call to a decidable problem can be replaced by an actual algorithm deciding that. That's a definition of decidable, and thus such an Oracle can be eliminated. Let me say that again. Any decidable or computable Oracle can be replaced by the code of a while program actually computing or deciding that problem, and thus can be eliminated. So that in this sense, sigma 1 is indeed just the ordinary semi-decidable problems that we already know to be equivalent, for example, to enumerability. And with a new definition, however, is pi 1. Pi 1 are the co-semi-decidable sets. Again, when pi 1 means k is equal to 0, means sigma 0 is decidable. And so this Oracle can be removed and can be eliminated. And co-semi-decidable means its complement is semi-decidable. So like, for example, the complement of the halting problem is not semi-decidable. So the halting example is an example of a problem which is semi-decidable, but not co-semi-decidable. And its complement satisfies the reverse property. The complement of the halting problem is co-semi-decidable, but not semi-decidable. So that explains further this level. Sigma 1 are the semi-decidable, pi 1 are the complement of the semi-decidable. But what is now sigma 2? Sigma 2, by the definition, are those that are semi-decidable with Oracle access to sigma 1 Oracle, that is to a semi-decidable set. And similarly, pi 2 are those problems that are co-semi-decidable with Oracle access to a semi-decidable problem, such as, for example, the halting problem. And here you already see that this now really increases the power, having Oracle access to, for example, the halting problem. And so to complement that picture here, to extend that, there's a next higher level, the union, that is the problems that are either semi-decidable or their complements are semi-decidable complements. And according to this lemma, the next level, level sigma 2, is the intersection of the delta 2 is the intersection of sigma 2 and pi 2, whereas the union of pi 1 and pi and sigma 1 is a subset of delta 2, so that the lemma justifies this picture. This is a proper inclusion, actually. And then we can climb up further. I already introduced sigma 2, those problems that are semi-decidable with Oracle access, for example, to the sigma 1 semi-decidable halting problem. And these are the problems whose complements are semi-decidable with Oracle access to, for example, the halting problem. And then there's the union, either semi-decidable or co-semi-decidable with this Oracle. And then there's delta 3 and so on. And this hierarchy keeps climbing up higher and higher, as we saw on the previous slide, with more and more higher and higher oracles. So, for example, here are the problems that are decidable with Oracle access to the halting problem. Here are the problems that are decidable with Oracle access to the iterated halting problem, h to the h, and so on. So this is a hierarchy of problems that are semi-decidable by Oracle while programs, where the oracles in terms are allowed only to come from a certain level, lower level in this hierarchy. So sigma k plus 1 induction means it's defined for sigma in terms of sigma k already being defined. So this is a typical induction step in the definition. And as I said, this is about semantic arithmetic hierarchy. This is called the semantic arithmetic hierarchy because it's defined by Oracle while programs and their semantics, their execution, meaning and capabilities. And the next slide will present you with a syntactic version of the very same arithmetic hierarchy, but syntactically now meaning without referring to Oracle while programs nor Turing machines as usual. So let's move on to the syntactic arithmetic hierarchy. And to this end, let us recall one consequence of the normal form theorem for ordinary while programs. The normal form theorem would say that every while program can be transformed into an equivalent while program that has only one while loop. Outside of everything, one big while loop, and everything else is just ordinary programs, ordinary loops, where the termination is implicitly guaranteed. And the consequence is that one can characterize, one can state that a problem is semi-decidable if L, if and only if it is of this form, belongs to all the steps in the integers x, to which there exists a witness y, it's called a witness, such that the pair x comma y, recall this is a Hilbert-Sotelo pairing function, belongs to v, where v is now decidable, arbitrary but fixed decidable set. Let me say that again. Semi-decidable means the set of elements to which there exists a witness, where the property of being a witness is supposed to be decidable. I'm not going to prove that and leave it to you to think about that. Observe that this is an equivalence, if and only if. Okay, and now based on that, we can now approach and derive the syntactic version of the arithmetic hierarchy, the same arithmetic hierarchy that you still see here on the right of this slide. Namely, first thing is we can replace semi-decidable by saying it's in sigma 1, because you recall sigma 1 means exactly semi-decidable with oracle sigma 0, and sigma 0 means decidable oracles can be eliminated. And now that is the starting point to our generalization. Now what happens if we replace sigma 1 with pi 1? Recall pi 1 are the co-semi-decidable, that is the complements of semi-decidable. And so by contraposition, being co-semi-decidable, being the complement, means we replace by De Morgan's rules, we replace the existential quantifier here with the universal quantifier, and we replace element with not element. That's De Morgan's rules, right? And that's what you see here, almost universal quantifier, except that I have not replaced element of V with the negation not element of V. But why have I not? Because it doesn't make a difference, because we can proceed from V to V's complement. It does kind of quell the negation here, and V's complement is again decidable, because as we saw, the decidable subsets are closed under complement anyway. So now we have obtained a syntactic characterization of pi of sigma 1 and of pi 1, the semi-decidable and the co-semi-decidable. And observe why I call it syntactic, because this is about logical formulae and their structure in terms of quantifiers. Here's only one universal quantifier, it's only one existential quantifier. And this is actually the explanation of why it's called sigma 1 and pi 1 here. Because as we now proceed and climb up to the next level, sigma 2 and pi 2, recall what is sigma 2? It's those that are semi-decidable with oracle access to sigma 1, to some semi-decidable, and equivalently to oracle access to some pi one because we can change the result of a query by post-processing. And this gives rise to this syntactic characterization. Sigma 2 is the set of all problems of the form with this quantifiers. There exists a y such that for all z. So now we have two quantifiers corresponding to this index 2. The first one is still an existential one. And the second one actually could be both existential and universal ones, but existential ones can be combined and summarized to this existential one, right? So several existential quantifiers can be combined into one block, and then the several variables can be combined into one single variable using the Hilbert pairing function. So it's no lossless generality to have only one existential quantifier over one natural number variable. And the second one is without the lossless generality, a universal one, where now the condition becomes that the triple X with the two witnesses Y and Z belong to V, where V is still some arbitrary but fixed decidable subset of natural numbers. So this is our syntactic characterization of sigma 2 here on the arithmetic hierarchy. Syntactic because you see now it's defined in terms of quantifiers in a logical formula. So this is sometimes also called structural complexity. Now, having characterized sigma 2 in this sense, what is pi 2? Pi 2 is the set of complements. And again, using De Morgan's laws means we can proceed to complement by inverting, by switching quantifiers. Existential one becomes a universal one becomes an existential one. And here we proceed to the negation, to the complement of V, but complement of V is still decidable, so that doesn't really change actually. And this is a characterization of pi 1, those problems that are co-semi-decidable with Oracle access to a halting problem or complement. And then you can guess what is sigma 3. Sigma 3 involves three quantifiers with three variables, quantifier blocks, but without a loss of generality, combined, compressed into one single variable. In the order existential, that's why it's called sigma, corresponding to semi-decidable, with Oracle access to a sigma 2, where sigma 2 now is captured by the remaining two quantifiers, and without lossless generality in the order universal existential, because otherwise quantifiers can be kind of subsumed and combined. So that's sigma 3, and pi 3 is with quantifiers reversed according to De Morgan. For all, they exist for all. And you can imagine what is sigma 4, what is pi 4, sigma 5, pi 5. So the entire arithmetic hierarchy is now recovered in this purely syntactic logical form, which is why I call this slide syntactic arithmetic hierarchy, as opposed to, and for you to remember, previous slide about the semantic arithmetic hierarchy, which was about Oracle while programs with iterated oracles, and the semantics, the meaning of while programs and the meaning of Oracle calls. So that sums up our discussion or elaboration on the topic of Oracle while programs and on the arithmetic hierarchy with its two variants, semantics and syntactic. Thank you very much.